Byzantine failures. I'm Giovanni Farina, and I'm a PhD student in a joint thesis between Sorbonne Université and Sapienza Università di Roma. Today, I'm going to talk to you about how to implement a reliable communication primitive in a distributed system affected by mobile Byzantine faults. This is a joint work with my advisors, Professor Silvia Bonomi and Professor Sebastien Tixeuil. Modeling a distributed system, one usually considers it as composed by a set of distinct entities named processes that aims to achieve a specific target. These processes are commonly assumed to be able to communicate between each other, for example through message exchange, and the capability of single pairs of processes to communicate is usually modeled with a link. The set of processes and all of their links constitute the communication network. Then, timing assumptions are considered for the specific system, and two of the main considered scenarios are the synchronous and the asynchronous case. In synchronous distributed system, all local computation and message exchange are time-bounded, in the sense that it is known by all processes how long it takes any computational step and any message to be exchanged. On the contrary, in an asynchronous distributed system, there is no time bound, namely the local computation and the message exchanged may take an unpredictable amount of time. Then, a model for a distributed system to be realistic should consider the potential occurrences of faults. Usually, one assumes certain kinds of faults that may occur in the system, for example, crashes or losses of messages, and that they may occur on processes, either on processes or on links. Now, to design a fault-tolerant distributed system, one usually establishes a set of assumptions and it designs solutions that succeed in achieving a specific target despite the presence of certain faults. Let us focus on faults occurring on processes. Among the kind of faults one can consider, the most general one is the arbitrary fault, also known as Byzantine fault. A Byzantine faulty process is one that can arbitrarily behave in the system. Of course, in order to design a fault-tolerant solution for a distributed system, there are additional assumptions to set. For example, does it exist a maximum number of faulty processes that may be present in the system, or do the faults occur only for a bounded amount of time? Or also, do the faults occur for a certain following a certain probability distribution, etc., etc. Now, all these ways of modeling process faults, in some sense, probably model internal misbehavior that may occur in the system. For example, data corruption, data losses, machine faults, and so on. But what about a virus or a malicious attacker? Usually, a malicious external attacker initially targets some weaker machines, and then, exploiting vulnerabilities that may be present in the system, it moves from one machine to another till reaching its target. Now, briefly, the literature concerning this kind of attacks can be split in two branches. A theoretical branch that investigates the fundamental distributed system problems concerning mobile faults, and a runtime branch which focuses on detection and reaction to external attacker. You can think as an example to the intrusion detection system. Specifically, several distributed system problems have been investigated considering mobile Byzantine faults. For example, the Byzantine and approximate Byzantine agreement, and also several register abstractions have been designed. All the solutions that have been proposed slightly differs on some specific assumption, but most of them assumes a complete communication network. It means that they assume all processes able to communicate with any other. Now, this assumption of a fully connected network does not capture certain distributed environments, and in these cases, reliable communication primitive can be implemented if certain conditions are verified. Basically, a reliable communication primitive allows in some sense to simulate a complete communication network on top of a general one, for example like the former in the slide. In detail, a reliable communication primitive is a distributed system protocol that, given any two processes referred with source and target, guarantees the following two properties, safety and liveness. The safety property guarantees that, if a correct target process delivers a message M from a certain source, then such a message has been sent from the source. The liveness property enforces that if a correct source sends a message to a correct target process, then such a message is eventually delivered by the target. The aim of this work is to investigate the reliable communication problem in distributed systems affected by mobile Byzantine faults. Let's start by defining our system model. We consider a distributed system composed by a fixed set of M processes, each associated with a unique identifier. Part of these processes are connected through reliable and authenticated links, constituting a communication network. The link assumption guarantees that the messages are not altered or dropped during the transmission, and that the identity of the sender of a message cannot be forged, so any process knows the identity of the peer that is sending a message to it. We assume that inside the system there may be up to F mobile Byzantine agent. A mobile Byzantine agent is an attacker able to move between one process to another through a communication link. Specifically, when an agent is on a process, he compromises it and makes it Byzantine faulty. We assume that the agent needs a certain amount of time to move and compromise a new process. In particular, this period is commonly referred with roaming pace, and it is known by all processes. We alternatively consider either that processes knew about a mobile agent that is moving away from them, and we will refer to this scenario with a where model, or that they are totally unaware of being compromised, and we refer to this case with unaware model. This modeling for the attacker is not new. It was initially proposed by Garai and then specialized by several others like Sasaki et al. Lastly, we assume a tamper-proof memory on every process, where the protocol executed by non-faulty processes is stored. So, at every moment, every process of the system either executes the protocol or is faulty and controlled by a mobile agent. Notice that the state of any process may change during the lifetime of the system, and any process can either be correct or Byzantine faulty infinitively often. Now, we previously saw that the standard specification for the reliable communication problem demands certain properties to be satisfied by correct processes. But we are now considering a system in which the state of any process may continuously change. So, first we need to answer to these questions. What is a correct process? In the sense that, what are the requirements a process needs to satisfy to be considered as properly executing a protocol? And then, what is a correct source? What are the requirements that a source of a message has to satisfy to be considered properly executing a protocol? We refer with correct source to any process that computes a message and it succeeds sending it to all of its neighbors. Then, in order to characterize a process that is properly executing a defined protocol, we provide a definition for a not permanently faulty process, that is a process faulty only for finite periods of time. We are now able to define a specification for the reliable communication problem with mobile Byzantine faults. Given a source and a target process, a reliable communication primitive has to guarantee the following two properties. Safety, if a target process is currently correct, so not compromised by a Byzantine agent at the moment, and it delivers a message M from a source, then such a message has been sent by its source. And liveness, if a correct source sends a message M to a not permanently faulty target process, then the target process eventually delivers M. This is the specification for the problem we aim to solve. Let us start by investigating the problem in an asynchronous system. Remember that in an asynchronous system, there is no upper bound on the time demanded for local computation and no upper bound on the time required to deliver any point-to-point message. We still consider that an estimation of the minimum roaming pace of the mobile agent is known by all processes and equal to ρ. So, is it possible to achieve reliable communication? The answer is no. The reason is that, given the absence of timing guarantees for the local computation and for the message deliveries, these may last an unpredictable amount of time. It follows that the mobile agents may continuously drop all messages transmitted by a source, even considering processes faulty for finite periods of time, because they can be continuously compromised and not being able to deliver messages. Therefore, it is not possible to ensure the liveness property or reliable communication in an asynchronous system affected by mobile Byzantine faults. On the other hand, a not-degenerated safe communication primitive that only guarantees the safety property can be deployed in an asynchronous system. I say not-degenerated protocol because also one protocol that drops any message exchanged in the system enforces safe communication. Thus, we target to a best effort solution that maximizes the number of messages correctly exchanged in the system. So, we show a safe communication protocol working in the aware failure model, in which processes are equipped with local clocks so that they are able to measure time periods comparable with the roaming pace. And of course, they have to know the value of ρ. I'm not going deep into the detail of the protocol, but you can get an idea looking at the picture in the slide. We allow a process to deliver a message if it has been received from more than 2 distinct processes in a time window shorter than the roaming pace ρ. In the aware failure model, we can assume processes that get free from mobile agents, wiping their memory, and so not diffusing spurious messages. Furthermore, we can reasonably assume that a mobile agent must remain on a process to force it sending a message till the end of its transmission. Lastly, we know that mobile agent must remain stable on a process for a period long at least ρ. It follows that a mobile agent that is moving in the system diffusing a spurious message cannot send such a message for more than 2 processes in a period that lasts ρ. It means that if a message is received by a process from more than 2 distinct neighbors in a period of ρ, then it can be safely accepted because it cannot be generated by mobile agents. So, we've shown that we cannot solve our problem in an asynchronous system because the mobile agent may prevent processes achieving the liveness property. So, we strengthen our assumption by considering a synchronous system. Specifically, we consider the same model introduced by Garay, a synchronous distributed system that evolves in synchronous round. In detail, these rounds are constituted by 3 phases: the send phase, where processes send messages for the current round; the receive phase, in which processes received all messages sent at the beginning of the current round; and computation, where processes execute a distributed protocol and generates messages to be sent during the subsequent round. We assume that the roaming pace of the mobile agent is at least 1 round and that they can only move between the computation and the same phase between 2 consecutive rounds. We start by identifying necessary additional conditions that must be satisfied addressing reliable communication. Specifically, in the aware failure model, reliable communication cannot be achieved in distributed system in which the number of mobile Byzantine agents is greater than or equal to 1/3 of the number of processes in the system. The reason is shown in the animation. As you can see, a process that is not receiving a message directly from its source cannot distinguish between a genuine message and one generated by a Byzantine faulty process. Moving to the unaware failure model, the lower bound increases to 1/4. Reliable communication cannot be achieved considering the unaware failure model in distributed system in which the number of mobile agents is greater than or equal to 1/4 of the number of processes in the system. The reason is similar to the previous scenario. A process that is not receiving a message directly from its source cannot distinguish between a genuine message and one generated by Byzantine faulty processes. We now finally define a solution to the reliable communication problem in the unaware failure model. We refer to such a protocol with RCMB, Reliable Communication Mobile Byzantine. This algorithm is parameterized by two thresholds, sigma and tau. We set tau equal to 1 and sigma to tau plus 1 multiplied by f. For sake of simplicity, we present our protocol directly on a graphical example on a fully connected distributed system with 5 processes where one mobile Byzantine agent is present. Initially, the source process, in this case process 1, sends its message to itself and all of its neighbors. Every correct process that receives such a message, it delivers it, because it has been received through a reliable authenticated link from its source. Thus, it can be delivered satisfying the safety property. Every message that is delivered by a process is stored in a set variable called delivered, and it remains there stored for tau rounds. Then, every process queues to be sent in the subsequent round every message that is in the delivered set, which is then removed according with the assumption of tau equal to 1. Meanwhile, a mobile agent compromised one process, in this case process 3, and stored inside its delivered set a spurious message that is also queued to be sent in the subsequent round. Between the first and the second round, the agent moves on a different process, process 5, and it forces it to send a spurious message to all of its neighbors. Process 1, 2, and 4 send a message diffused by 1 to all of their neighbors. Then, at the end of the second round, all correct processes receive more than sigma copies of the message of the source, and at most sigma copies of the spurious message. Thus, the former is delivered by all correct processes, and the latter is discarded. The RCMB protocol enforces safety of reliable communication in the unaware failure model, considering sigma equal to tau plus 1 multiplied by f. Indeed, in the system there are at most sigma processes that concurrently send a spurious message injected by a mobile agent. Such injected message is dropped by a previously faulty process after tau rounds. The RCMB protocol enforces liveness of reliable communication in a fully connected distributed system in which the number of processes is more than 4 times the number of mobile agents. Moving to the aware failure model, the RCMB protocol simplifies. Specifically, messages do not expire in the delivered set due to the assumed aware failure model, in which processes can wipe their memory when they get back correct. So, we defined RCMB protocol that achieves safe communication assuming certain values for its threshold sigma, and reliable communication in complete communication network. As a matter of fact, there are several network topologies where RCMB can be employed targeting reliable communication. The first topology on top left has been identified by Sasaki et al., who showed that reliable communication can be achieved in graphs G alpha beta, where alpha is the number of disjoint paths available between every pair of processes and beta is their length. They proved that for certain values for alpha and beta, reliable communication can be achieved in the unaware failure model. The figure on the top right represents a minimum k-level ordering topology. In such a network, the nodes of the graph can be partitioned in ordered levels with respect to a certain node, such that all the neighbors of the defined node are in the first level, and all the others are in a level such that any vertex has at least k neighbors in the previous levels. The concept of a minimum k-level ordering can be specialized considering levels containing a certain number of nodes, as in the example depicted in the bottom right. In these networks, reliable communication can be achieved considering certain values for k. Lastly, in the figure on the bottom left, you can find an example of a k-click community network. This is a topology composed by cliques of k nodes that are all adjacent one to another. Again, reliable communication can be achieved in these networks considering specific values for k. In the paper, there are collected several sets of assumptions enabling reliable communication in these networks that are not presented here due to time constraints. In conclusion, we defined and investigated the reliable communication problem in distributed systems affected by mobile Byzantine faults. As a matter of fact, we placed it in an extreme scenario where the attackers compromised new nodes at the same speed of the message exchange. Further investigation could generalize the attacker, either considering a more realistic compromise speed or probabilities of compromise. Furthermore, the communication primitive could be extended considering self-stabilization, namely considering all processes and links starting the execution from an arbitrary state. Thank you for your attention.